think one categorization that is useful for this workshop is maybe starting from the optimization problem. We all maybe have an idea of kind of an optimization model that we want to solve that answers some of the questions we have related to infrastructures, individual technologies. We have kind of an objective, maybe minimizing costs, subject to all these different technical constraints. So on a kind of mathematical understanding, we have an idea of what the optimization problem should look like. And often these problems that we formulate, they're easy to formulate and say, oh we want to minimize costs that supplies our energy system for all the different sectors in all of Europe. And that is a very complex problem. And we need some tools at various ends of finding the answers to this optimization problem. So one problem is, of course, the data. We need to bring in some data from various different fields, like from the climate data, historical weather data, to the infrastructure data. This, for example, TSO here in the back. Like we need data on the power grid that currently exists to make an assessment of what new infrastructure we need. And this is what most of this morning's sessions will focus on, kind of bringing in data into this optimization problem. And as an intermediary step in between, from processing the data into an optimization model, we maybe have another layer of abstraction that kind of gives us a standard of how to formulate an energy-related optimization problem, gives it in certain standard data structure, representing standard components like different types of power plants, grid components, storage components, and so on. And that is what, for example, PyPSA does. It's a kind of Python package that provides us with this standard data structure that we can kind of process all our raw data into a fixed standard format for the tool that then parses that into an optimization problem. So that's kind of the inflow or the tools that we need and the processes that we need on the inflow side of formulating our energy system model. And then there's kind of a secondary step where we have now a data-rich, heavy optimization problem, and we need some tools and algorithms to solve this model. And so the PyPSA or any other kind of energy system modeling framework needs to use some other tools, like, for example, Pyomo in Python, LinoPy, that is what PyPSA uses in the back end, or if you're Julia in the Julia world, for example, JUMP. That is another layer that takes energy systems data and formulates an optimization problem out of that different types of solvers can communicate with. And different types of solvers may be open source solvers, like HICE, for example, is very popular in recent years, but often it can be also commercial software that solves a kind of very clearly defined task of kind of you have the objective, the constraints, and in the end get some information on the decision variables, but also information about the sensitivities that the model has, the dual variables, the shadow prices, that we can then in the end use to interpret that. And that's maybe the last kind of category I want to mention, is that once we have solved a complicated model, we need reasonable ways to kind of get statistics about the network quickly, process this data, and maybe also visualize this data. So out of all of these categories, we'll cover most of these, I would say, one way or another. But we want to start with the data inflow today, before talking about the kind of model formulation, the optimization problem, and so on. And we actually want to start with the electricity system. So we start with the electricity system. First of all, it's because historically PyPSA Europe has been originally formulated as an electricity system planning problem, and we've kind of tagged on the other sectors as we as we noticed, well, that's going to be very relevant for the electricity system to know what's going on in the other sectors, and that's how also historically PyPSA Europe has evolved into becoming more of an energy system modeling rather than a power system modeling. So the name PyPSA is a bit of a misnomer because it should be Python for energy system analysis. But it's too late to change it now, so we have to live with what we have. That was the prequel. And just a kind of another administrative note, feel free to interrupt me at any time if you have like a question about one of the slides, a specific aspect that you're interested in. I'm happy to jump ahead and jump back and also talk about things that are not on the slides. So just really welcome, just raise your hand and I'll find the right time to take your question. So generally, I mean, it's been mentioned in some of the introductions of the people involved in this training, but we're mostly kind of related, we're mostly interested in these infrastructure questions of how do we make a system, a continental system work that is highly interconnected, has high shares of variable renewables with different temporal characteristics on the supply side, but also on the consumption side, quite a bit of temporal dynamics as well as spatial dynamics across different sectors, not only electricity, but also heat, transport and industry transition, and a lot of interacting parts. So so it's very difficult to assess the value of a specific technology without having covered also the competition of this technology somewhere in the model. And it's very difficult to disentangle different aspects because they're interacting feedback loops everywhere in the system. So what we typically do is that we put all of that into a single optimization model that then co-optimizes the investment decisions, the siting decisions of different generation, storage, conversion, and transmission infrastructures across different energy carriers, but also the operation. You can do optimization problems of operation only, like market modeling, but you will never be able to do sensible investment planning without also considering the market dispatch side in the back end. So all of this, so we have kind of over the years built this kind of deck of different tools that help us formulate these large-scale energy system modeling problems. Some of them are about data processing, bringing weather data into energy systems data, collecting different open data sources and making sense of them, but also on the algorithmic side. We are always concerned with this question about how much detail can we bring into the model, how much detail is necessary to bring into the model, and what are the trade-offs between tractability of the models and accuracy of the models, and where can we kind of cut details to make another dimension be represented in more detail. And certainly this varies a lot between the different use cases, and that's also why one of our goals is to make this model more and more configurable, so that, for example, if you're very interested in the temporal domain, then you can bring in 1 year, 2 years, 3 years of data at hourly resolution, but then you have, for example, to cut on the spatial resolution of the network, and you can make these trade-offs on your own as you see fit. We always say that the most interesting things people do with the model is not what we do in our research group, is what other people do with the tools. And over the years, there've been quite a range of different examples of industry companies, so TSOs like Transnet BW and APG, so Austrian power grid operator, and kind of southwestern German power grid operator, have done a series of kind of more conceptual long-term studies with that. there's a range of different NGOs who particularly kind of pressured to use open source tools rather than commercial tools or costly commercial tools to do these analyses, and also international or governmental organizations, like there was a redispatch and congestion management study done by JRC. There was the IEA had some studies on this managing seasonal variability of the electricity supply. And there are some quite nice examples of Amber, for example, in the UK. We were quite involved in kind of the Labour government energy strategy, kind of devising that strategy, as well as in Poland, in PL, for example. There's also been kind of an example of a regulator, like Canada Energy Regulator, who's done a Canadian model version of the tool. That brings me maybe to another kind of development that we see currently, is that there's, for example, PyPSA-Eur, which is going to be the focus of this workshop. There are other people who have developed kind of a global version of the model, PyPSA-Eur, and there are a lot of people around the world who, like, for example, here we've seen this this example of PyPSA Spain, for example, where people either make a derivative of one of the existing works with kind of detailed data on the country they are focusing on, or completely new models for their own countries. And we try to keep a list of it. We don't always know what is around there, but and it's also not very coordinated. So it's kind of a grassroots movement, maybe, that has really no coordination. There's just people picking up the tools and making them as well available as well. So, for example, for Great Britain, for the UK, there are, I think, 3 different PyPSA versions out there that have been developed independently by different people. So, just a quick rundown of the kind of classes of optimization problems that you can solve, and what the main components is, and what the general structure of the backend is. We'll have some time, I think, this afternoon and tomorrow morning, when Igor goes through the details step by step, and more goes through it in a more code-based manner, less abstract than I show it here on this very wordy slide. But maybe let's go by column and maybe go backwards. So what is in the backend? So we think that, we thought that if you're working with Python, you know pandas, and so most of our data structure is built around pandas. We've at some point thought about, using more computationally efficient data structures and so on and so forth with the bigger models, but then we thought it loses some of the accessibility that pandas offers, because everybody knows that. So it's something that, something everyone can start with. It's really, originally we used Pyomo, and at some point we ran into memory bottlenecks for the really large problems. Particularly the memory, but also the time of building the models was a particularly important, particular problem. So we've, people in our group have developed LinoPys, also Python-based solver interface that can just interface with different solvers. So it's easy to switch between the different solvers depending on what license you have at hand, for example. And with that, we've basically narrowed down kind of so basically most of the time and the memory peaks that we see when solving the models is now purely what the solver does. So it's like 99% of the time spent in the solver, rather than spending 20% of the time just building the model. And also the memory peaks, they are then basically kept to what the solver will use. So that's sounds all nice, but maybe there should also be highlighted that it's really, so there's no GUI, for example. So you need to touch, at the moment, you need to touch code in one way or another to use these tools. There's no kind of drag and drop interface to connect components, and also for building the model workflow, you need to get comfortable with a command line, at least. Currently, we have some ideas about because we're a small maintenance developer team, we don't have time to model the GUI or to develop it. But maybe with the advent of AI, it's maybe some kind of AI interface or chatbot interfaces that you can do with PyPSA for kind of smallish problems. So we'll just see. We're just experimenting and see how it goes. So the components that it has, so just basically categories of components in the energy system that come with different sets of equations. There's components for electricity transmission networks. There's components for conventional generators with kind of unit commitment constraints like ramp limits, up and down, startup and shutdown cost. Of course, everything is trimmed to work well with the challenges of a highly renewable system, like variable generation with time series, storage with efficiency losses, inflow and spillage for the hydro. And what's become very, very important is the conversion between the different energy carriers. And not even only energy carriers, but you might even put steel or CO2 in as carriers that then represent more of a material. And we're currently, without really having the intention to do it, migrating from originally power system model to an energy system modeling, to an energy system model to an energy plus material flow model, just because some of these questions are so interlinked. You have a lot of energy carriers that end up in plastics that are very energy intensive, just to name an example. On the left-hand side, as I said before, you can do market modeling on its own. You can do capacity expansion as an extension of the market modeling. And on the capacity expansion side, users generally have the choice between optimizing for a single horizon, so just looking at a kind of target scenario of 2050, how the system might look if everything can be optimized perfectly, as well as doing these multi-horizon optimizations where you have a set of different investment periods, like from 2025, 2030, 35, and so on towards 2050, where different types of investment decisions are taken at the various stages. And there's also an option to do that kind of with perfect foresight as a single optimization problem, but also kind of myopically going step by step. On the market modeling side, it's not kind of pure economic dispatch or market modeling. There's kind of power flow equations in the back end. So it has these typical models of linear optimal power flow, so kind of linearization of the nonlinear power flow equations, plus some additions to the normal DC or kind of linearized power flow equations, in that we add a loss approximation that then matches even better with what you would get out of a nonlinear power flow simulation. So all the problems that you can do in PyPSA are linear at the moment. So there's no nonlinear optimal power flow at the moment, and I don't think we are going to develop it. Maybe somebody else will do it. We don't know. But basically everything is linear. And for these large capacity expansion models, everything will be continuous linear problems. But if you're looking more in operational settings with, for example, the unit commitment constraints, then you will have also the option to have this formulated as a mixed integer linear problem. But these are, and if you have, for example, some demand elasticity in the objective, you may also end up with a QP problem, so quadratic problem, where one of your terms in the quadratic in your objective function is quadratic. But these are the three main classes of optimization problems that you can solve. And yeah, there's other things like, for example, n-1 constraints on transmission lines that you can put that add extra constraints to the model. Good. I don't see any. There's a question? Yes.
What is included into the redispatch that we mentioned in the market modeling?
Yes.
In Germany, we have dispatch 1.0, 2.0, is 5 or?
We basically have a very simple example how conceptually you would set up the kind of model as kind of solving in two stages, like clearing a market at a single bidding zone and then rectifying doing the redispatch, ramping up and down certain resources, but it's completely up to the user how they want to model that and what components they want to allow to react. Yeah, but it's more of a kind of new in development beta phase feature, and not really a built-in feature, but just kind of an example instructions how with the existing set of functionality you would model that. Yeah. Any other questions so far? I don't see any. So that's kind of the data structure side, but here's where the data comes in. That's PyPSA Europe. PyPSA Europe is not a Python framework. It's not a PyPSA package, but it uses Python code to orchestrate a workflow that processes all the different kinds of raw data. I named some samples earlier into these highly resolved energy system models. So what we can computationally achieve is maybe something that has 1 hourly, 2 hourly, 3 hourly resolution for a year, in combination with the capacity expansion of the network, the placement of the different assets of supply and consumption across different network layers. For example, the electricity here, the hydrogen here. And I think we'll see some more examples of these maps later. But the general principle of these maps is that you have different layers of the network components. The upper half circles here would tell you about the supply situation. So see here, there's a lot of kind of wind in Denmark, and then there's a lot of solar in Spain. So far, so good. I think nothing surprising to anyone here. But then the model has freedom in placing the electrolyzers, for example, in the different regions. So it's quite a bit in Spain, where the electricity prices are low, read out from the shadow prices of the optimization model, but also some in the kind of greater North Sea area. But just kind of, it's not a definite answer. It's just an indicative, kind of illustrative result here. But then you have these large consumers of the electrolyzers here on the one hand. Then you can go to the different energy carrier network layer and look at how the hydrogen is produced and consumed. So then maybe not everything will be green hydrogen. Maybe you see some bits of gray, blue hydrogen here and there. And then you wonder how and where is the hydrogen used. So the lower half circles on the hydrogen side, it's mainly green and bluish bits. So that would be synthetic fuel production for Fischer-Tropsch, methanol for shipping, for making plastics, and so on. And you see some transport dynamics here. And it's not always easy to understand all the dynamics, why the model does the things it does. But eventually one can get a rough idea why the model does these things. And all of these spatial trade-offs in infrastructure build-out is always kind of subject to the temporal resolution of the network, about kind of how flexible do the electrolyzers run, subject to their capex, for example. Okay, so that's a very good question. So PyPSA Europe idealizes a lot. So it doesn't represent, so it's generally not very good at representing the current regulations, current setup of the different markets. It has been very future-oriented in the past and very idealistic about the market coordination mechanisms, both on the temporal side as well as on the spatial side. So an underlying, or it's not a conscious assumption per se, but an underlying assumption of how we interpret the energy balance shadow prices of the energy balance constraints in the model from the optimization model. It's basically equivalent to assuming nodal and dynamic pricing for all the different assets that are part of the network. So it's an important question that you ask, is because one has to be aware of that most of these infrastructure coordination questions that the model optimizes are relying on this form of coordination. It's not directly saying that you need exactly this market setup, but if you don't have this market setup, it's likely that you will need some kind of intervention, either through setting up this market in this way or coordinating that through other mechanisms. But it's not like, I mean, that it's an optimization problem after all, where the different parts of the network work very well together. Yeah. So, so your question was about the market setup in general. So what we have in mind is to implement some of the currently existing euphemia flow-based market coupling in Europe, and I understand the Nordics also joined the flow-based market coupling recently. So I think in general we've been very future-oriented in the past, and we're kind of slowly moving to more short-term questions about the development of prices in the system and so on. So, but that's I'm not going to promise that for next month. It's going to be maybe a year or so until we have that. It's not quite clear how we have that. Yeah. Yes. So if you have, if you have the capacity expansion in the model, then it can be that in scarcity periods you can see the capex marginal the capex show up as marginal cost. Yeah.
Since we know like hydrogen and methane can be used in various sectors, like as you mentioned, plastic, synthetic fuels. So how to estimate their demand, because it's I checked the Eurostat data personally, but it's not there. Like, what will be the plastic demand in 2050? So,
okay, I would defer your questions to tomorrow, because it's very kind of sector coupling oriented, and we'll go into detail about kind of how we get to the demands for the different energy carriers. Okay. So briefly go over the slide, which is you've seen this type of problem one way or another. Just to highlight that what we optimize for is typically some kind of yearly system cost. It might be different if we have multi-period planning that includes both the kind of annualized capital cost and the marginal cost. And as we progress from today's system, which maybe leans a little bit more heavily on the marginal cost side, we kind of move towards a system that has kind of leans heavier on the capital cost side. We pull all of that together to minimize the total annual system cost, subject to the kind of usual constraints about the kind of technicalities of the transmission network, the wind and solar availability time series, the capacity geographical potentials for the renewables, then where you use some of the flexibilities from various different technologies like gas turbines, battery hydrogen storage, HVDC links, and more that we'll discuss in detail tomorrow about various levels of sector coupling, and all subject to reducing some form of emission reduction target. So while both is possible, we typically set a constraint for the total emissions for the whole system, and then read out the shadow price to interpret that as a CO2 price, like in the ETS system. It's also possible to put a CO2 price in the model, to do it kind of the other way around and kind of not have a strict emission reduction targets, but typically our working mode is here to set a CO2 emission reduction target. But so far so good. I don't think there's kind of too much new things for all of you, given that you all have some experience with energy systems. So our general approach. So how do we bring the raw data into a model format, and what tools do we use to help us with that? And for that we use a tool. It's called SnakeMake. It originally comes from the bioinformatics fields. So if you look closely at I don't know if it's large enough for everyone, but if you look closely at these elements here in this graph, it just has nothing to do with energy. It's like align to genome, index genome. So it's another very nice example of an open source tool that has been developed by it also comes from academia, where people have just seen the use to easily connect interconnected longer pipelines of data processing, where we have just been the beneficiaries of having this tool available and using it for the field of energy system modeling. And that really makes it much easier to work with a variety of sets of data sets. We don't have a guideline of so like for new users that first you have to run this Python script, then you have to run this Python script, and then the other one. And once you have all of this, then you have to move some of the files into the correct folder. No, we don't want that because it's very difficult. It's error prone and it's difficult to explain to anyone. So it's all kind of automated in a clear structure where you have basically each of these elements in this graph is a Python script that is isolated. It has a clearly defined input, has clearly defined output, and by connecting inputs and outputs, the graph here can automatically be built, and the model can even automatically determine if, for example, I have run this workflow at some point and I ended up here at the end, and I changed some code here. SnakeMake would notice that, this data here is still up to date. I changed something here, so everything out here might be updated. So if I change something here, I should rerun this, this, and this, for example. That's also kind of reduces the load of the processing data. Kind of once you have, it's a little bit like a caching mechanism, where once you have run a part of the workflow, there's reduced need to rerun everything, and just helps us kind of isolate different aspects of the modeling in different rules, and helps with reproducibility and distributing runs for many different scenarios. We don't want 1, 2, 3 scenarios. We want to run hundreds of scenarios. So that's here now a code view of how this workflow is built. So I mentioned here basically in this graph, every node is a rule, is a script. So in SnakeMake syntax, you have these rules that describe a certain task that have a clearly defined input, for example, a text file, an output, maybe again a text file, and a script. And there are various other things that you can tag here, for example, how much computational resources it needs, like the memory and the number of threads it can be using. But these are the 3 basic inputs. And then you maybe have a different rule in the text file, which has as an input the output of another rule. So that makes the connection to build this graph structure. And that maybe produces a figure with a different script. And when I enter the terminal and say, SnakeMake should build me this file, so the output of this file, we'll say, okay, to build this file, I need this file, and this file is created by this file. So I first have to check, is this input data available? Run the script, produce this output, and so on and so forth. So that's how the automation works in code. And I think it's not only nice for automation, but it's also very nice for documentation in general of the model workflow. So this is how the electricity part of the workflow looks like. And you don't need to go through every single element, but there's bits about retrieving. There's bits about building the transmission network. There's bits about building the electricity demands. There's bits about determining the renewable profiles, adding power plants, and clustering the network. And my goal would be, before you get started on your laptops, to walk you through this electricity part of the model, step by step, broken down into these 4 segments, or 4 segments. The 5th one we'll talk about tomorrow. from automated downloads to processing the data to pulling everything together into an energy system optimization model, and then solving, summarizing, and visualizing the results. So that's the rough structure. And for all the different data, or for all the different aspects of the workflow, like the renewable potentials, the power plant data, the grid data, we have to access different set of data sets, and that's just a kind of showcase of some of the data sets that we use. So there's two main weather data sets that we process. It's this ERA5 reanalysis weather data that we use for temperature, wind speeds, runoff data, and then we use the SARA-3. It's a satellite-based weather data set, which has a little higher accuracy on the solar. For example, the cloud coverage is represented much better in this kind of satellite-based observation. And in principle, this data, I think this data by now is available for 85 years in principle, and the SARA-3 also for 40-ish years. So that's the weather data aspects. And for identifying where the potentials are for the renewables, we tap into a series of data sets, for example, where natural protection areas are, where the different land types are. So maybe here the red bits, you can see London, for example. You have kind of urban areas where you maybe need to implement a setback distance. You have shipping lanes offshore where you need kind of to keep a distance for offshore wind developments, as well as kind of water depth determines whether you can still do fixed pole offshore wind parks, or you need to go with a floating route. The grid data we take from OpenStreetMap. That's going to come on the next slide, and most of the energy balances in the data set, they come from kind of country level annual statistics like the Eurostat or the JRC IDEs database. And the model then uses other data sets that we'll show later to distribute these annual country level data sets in the temporal and the spatial domain. Yeah, we often have this. We mix in different data sources to achieve data on a specific aspect of the model that covers both, or that matches the spatial and temporal resolution of the model, even though we maybe don't have kind of one data set that delivers this data at that spatial resolution. Right, and maybe the last thing I want to highlight here is, for example, global energy monitors has been kind of one of my favorite discoveries in the past 2 years. It's a super nice website, super nice data sets, not only on power plants across the world, but also has very good data on, for example, LNG terminals across the world, steel plants across the world, and has very detailed on each of these, for example, steel plants. So it has data on the production capacities, when it was built, when it was last relined, for example. So it's a very extensive data set, and we're happy about any other data provider where we can source data from. So what you see here in general is that you will not see many country-specific data sets, just because we always, we are modeling Europe, not the European Union. So we already have Switzerland, Norway, and the UK, and some of the Balkan countries that we need to supplement with. But if you imagine that we have to if there were better country-specific data sets, we would have to do it for 30+ countries across Europe. And I think that's just a general kind of bottleneck in the development team, that we just, even if there were more accurate data, we don't have the resources to bring it into the model. And I think that's also some of the motivation why my folks build kind of derivatives with more detail on the specific focus regions. Okay, so everything starts with administrative regions. So country boundaries, the exclusive economic zones, and some of these specifics are given in this NUTS nomenclature. So everything starts with that. And because PyPSA was originally built as an electricity system model, one of the first steps that the model does is to construct a base high voltage networks with kind of the substations, the transformers, AC, DC lines, and does some calculations about the capacities, maybe perhaps dynamic capacities, as well as supplementing some of the set projects in the TYNDP 10-year network development plan. So if you go, for example, to this very nice website, Open Infra Map, actually, can we do that? Can we go to Open Infra Map? So we just break it up a little bit. And who would like to zoom in into their hometown? Okay. Berlin, okay. Berlin is quite interesting. So this is a website somebody has built based on OpenStreetMap data. Okay. It's maybe too far in. Yeah, that's very... Okay, so we zoomed into a power plant directly. That's Berlin-Marzahn power plant. And you can see there's a 110 kV line coming in. There's an Umspannwerk, so transformer station. And there's, I think this should be I think this is a 220 kilovolt line. And if you zoom out a little bit, you can see how that then goes to one of the very few underground AC transmission lines in Germany that crosses Berlin, 380 kV, I think double circuit, Transversale Berlin. So it has roughly equal accuracy across all of Europe. If you zoom into Galway, for example, you don't need to do it now, but if you zoom to Galway, there's been someone contributing grid data connecting the individual households, so you can really see how the different households are connected. Not every country and not every region has this level of accuracy, but just to illustrate that this is a community effort and that basically anyone can. It's a bit like a Wikipedia. Anyone can add data here, and once it verifies, it's there. And we've built PyPSA Europe in such a way that we can, from one day to the other, so sometimes we maybe spot a mistake in the data, we correct it, and then we rerun the PyPSA Europe workflow, and we have the updated grid data available.
So, in terms of reproducibility,
Mm-hmm. Yeah.
How do we know what's been changed between my last update and this one?
Yeah. So there's different modes of operation in PyPSA Europe. So you're right. You want kind of a reproducible set of data. So we relatively regularly run this network building process, and there's some data cleaning that you have to do here because sometimes from the data it's not directly clear how they are connected, where we then put the kind of checked and validated version onto Zenodo. And that's what most users, unless they actively want to update the topology and kind of source that and rerun that themselves, they will use a versioned version of the grid data. Yeah, that's an important point. Okay, I think we can go back to the slides. That's one bit of the data. And the other bit of the data is this, I think most of you will, or many of you will know this map. Is kind of a map of, or a list of network development projects that we add onto the network. And it's also configurable depending on what kind of what year of data you want to, what year you want to look at. Maybe you want to model a historical year of 2019, 18, or something like that, and then of course you don't want all the tuber NDB projects already in the model. But if you do that across all of Europe, you get basically a network of maybe 6,000 buses and 7,000 lines, a couple of HVDC lines. And from the OpenStreetMap data, you get data on the kind of topology, the number of circuits, for example, and the voltage level. But one thing that you don't get is the data about the impedances, for example. And there are a couple of data sets out there, like from the static grid model that have this data, but it's not exactly georeferenced, and it would be quite a bit of manual labor to put that in. So what we use currently is kind of a set of standard line types, kind of standard component, or standard electrotechnical characteristics of a typical, say, 380 kV line, 220 kV line, 300 kV line, or in Ukraine, for example, a 750 kV line. What we also calculate, and maybe touch upon that later, is that the user has the option to allow some grid enhancing technologies. For example, the dynamic line rating that is processing some of the weather data, that then results in higher grid capacities if it's very windy and cold, so that lines can be loaded higher. So that's also a calculation step that happens before we do any clustering, because quite the orientation and the routes of the transmission lines are quite relevant for determining the dynamic line rating potential. But what happens afterwards is, because we cannot solve this 5,000 node network with 7,000 lines for the capacity expansion model. We maybe can run it operationally at that resolution, but then it's also the question whether our data distribution heuristics are accurate enough to run it at this 5,000 node resolution. So I think the maximum we've done in the past is like 1,000 node resolution. So at that stage, we don't really add any time-dependent data yet, unless we need it for the clustering or the kind of like the dynamic line rating, it requires it. So the time series we add later. Yeah. So it's mostly about grid topology first. And one of the first steps that we do, also because we don't have too good data on the transformer capacities, is that we transform everything virtually to a 380 kilovolt level that removes all the transformers in the network. And you can think of it maybe like that the 220 kilovolts line may be equivalent in transmission capacity to a third of a 380 kV line. I don't have the exact number in my head, but kind of you do this transformation of the capacities, but also of the impedances to the new voltage level. And then you can apply different clustering algorithms to reduce the network size. For example, k-means or hierarchical, and you can use different attributes of the network to cluster the network. You maybe want to cluster regions together that have similar renewable profiles and potentials, or you maybe want to cluster together regions of the network that have no transmission bottlenecks in the system, because then it doesn't matter so much that you kind of copper plate or kind of muddle all of these substations together if there's no transmission bottlenecks between them anyway. Right, so that's the transformation. That's how the network looks like after the transformation. Just the colors disappear, and then we can, just in the configuration file, we could set whether we want 512 regions, 256 regions, 128 regions, 64 regions, and the minimum, I think, at the moment, if you have a coverage of all the different regions, is 41 regions. So why 41? So it's at least one node for every country. And if a country like Denmark has 2 synchronous zones, it needs to have two nodes, one for each synchronous zone, because then you have the interconnectors between the regions. You can go lower, but for that you have to reduce the coverage of the model. So you can also say, for example, you only want to model the Nordic countries as something that you can then configure in the configuration file. And you can also say in the configuration file that maybe I want to go with maybe I want to go with 128 regions, but my focus country is Ireland. Then I could also go and say, well, I want 50% of the nodes distributed in Ireland, and the rest of the countries has then a reduced budget for distributing the capacities. The nodes per country, they are proportionally assigned to the kind of energy demand of each of the countries, and then there's the exact clustering of the different which regions belong together is then done on a per country level. And that just ensures that you don't get clustering of network components across country borders, because that would cause other problems for us, because we want to maintain the country level statistics. So if we have, for example, put Belgium and the Netherlands together, then we can't really say what the energy demand in Belgium would be, or vice versa in the Netherlands. Okay, all right. So far about the clustering.
There's plenty of compute there, but what about the interactions with the compute which are not considered? For example, when, I don't know, there is a huge solar park in Morocco or something like that, and comes a lot of energy from a neighboring country, which is considered. What is the assumption there?
Okay, so we've done a study on imports, and we've given the model to import different types of energy carriers, including electricity. And there's definitely a preference to import some kind of fuels, first of all, rather than electricity. And there's a configuration option in PyPSA-Eur. It's currently relatively simplified, where you can say kind of import costs for certain types of fuels, and like for methanol, for Fischer-Tropsch fuels, for ammonia, and then once you go to hydrogen, for example, and LNG, then the model will use the kind of sites of the LNG terminals as potential entry points, or some of the existing pipeline connections. We've kind of excluded the paths through Russia, for example, but kind of you have some connections in southeastern Europe as well. So there is some option for interconnection, but it's mostly not electricity based. Also, I think for that one would have to, because it's also a bit it's challenging, because you don't want these satellite regions to be aggregated too heavily in their time series, just representing them as a single time series, because then they seem so much smoother than a highly spatially resolved network on the side. So it's a bit tricky from modeling inside. I think so. If
you want to model up to 2040, how do you do it with the transmission capacity expansion? Because there are also planned interconnectors, right, between countries.
Yes. So what we typically do is that we don't put in the exact capacities of the TYNDP plans, but we put in the topology options of the kind of routes that are thought of at the moment, and And I think, I mean, in general, the network is already heavily meshed, and I think the most relevant topology changes will be kind of long distance point-to-point HVDC connections, where you don't have too many. It's relatively controllable power flow in the network, so that you don't have the problem with the loop flows, for example. In that case, that would make it difficult to have them as decision variables, whether you build this line or not, and then you change the topology and Kirchhoff voltage laws and so on. So yeah, but in that sense, we just add the HVDC topology options in the network. Does that answer your question?
And that's integrated in PyPSA-Eur already. So if I say I want to model the horizon from 25 to 2040,
yeah.
Is that integrated or is that step?
That is integrated. I think what is maybe not so well tested yet is the kind of how the transmission lines that are planned to come online, that they come online at the exact right times in the horizon. We just haven't modeled that in quite a while, so no guarantees on that side. Yeah, but in principle, either way, it shouldn't be too much of an effort to put it in. There was an, yeah.
So you mentioned that it's possible to do more in detail grid in some part and cluster the other parts. So what are the limits of this? For example, if I want to model a specific region and I don't really care what happens anywhere else, but in the way that it affects my region, is that possible to do? And is there a way in PyPSA that helps you do that, like to make the clustering adequate?
Yeah, I mean, you can play through different clustering algorithms. You can you can tweak the spatial resolution and zoom into certain focus regions. So, for example, you can also say if your focus region is Spain, you maybe also want Portugal relatively highly resolved, and France, and then the further away you go, you maybe have fewer nodes. So you have fine-grained control over that, how many nodes in kind of satellite regions you want represented, or you just exclude them overall and then they just disappear. Yeah, that's the level of control that you have. Okay. Okay, so renewable potentials. 2 steps, calculating where's the area available to develop different types of renewables, and second step, then based on the where the areas are available, what the capacity factor profiles would be per region. And for that we use this ADLAR tool that's been developed in our group kind of 10 years ago almost, I think, where we just it's all about converting weather data into energy systems data, not only the supply side for the wind and the solar, or different types of solar, like there's features for axis tracking solar as well, but also the heat pump coefficients of performance, for example, the dynamic line rating, the heating and the cooling demand. So everything that is kind of weather related, it goes through this tool. And does not only do that for the time series, which is illustrated here, but also for the land eligibility analysis. But if we stack to the time series here for 1 second, it's just a kind of animation of how we go from the weather data to the capacity factor data. I think it's a relatively simple setup. I think there's kind of some room for improvement if that's really your kind of focus topic, but it takes just standard solar panel and wind turbine models, applies a power curve, takes into consideration the surface roughness to scale the wind speeds to the hub height, and then can use kind of one of the historical weather years that are available. In principle, there are 84 years available, but downloading that data is sometimes a bit tedious, connecting to, especially since they have changed their infrastructure recently. So what we provide here on Zenodo, again, is a set of, I think by now, 7, 8 different weather years with different characteristics. There's, for example, 2020, which had very favorable wind and solar conditions. There's also 2010, which had kind of a challenging Dunkelflauten period in it. And the results, the results vary quite a bit depending on what weather year you use, which is maybe an indicator that we should use more than one weather year in the energy system models, but that's kind of also a computational frontier that we see in the energy system models.
So that benefit on the node is that takes wind speeds and then processes based on the type of turbine.
Yes, so it's basically on the node what's hosted is the kind of influx, the wind speeds, temperatures, and so on, and the processing, because the processing from the raw data to the regional capacity factors, it also depends on where the areas are, because it does not make sense to take an average, including the regions that are not eligible for solar development.
Would it be easy to use a tool that does not act like to generate the temperature? For example, when they try renewable energy, I see it works the same.
Not so easy. I mean, I can say in principle, yes. In general, if you ask me throughout the workshop, is it possible? I will always say yes, because with enough resources and coding power at hand, you can do these things, but I can maybe also give you an indication of how easy it is, how much work it would be. So, so it's easy in the sense that you would just, and that goes in general for PyPSA Europe, if you mirror one of the outputs of any of the rules, they can be taken by any of the consuming rules. But the data sets, they are not, especially the intermediate data sets, they are not really standardized. So yeah, it might require some data wrangling, and so far I don't think anyone has ever kind of exchanged the weather data with some other data sets. But in principle, it's an X-ray SCDF file that would have to be changed there. Yeah.
Just a question. Considering future climate change projection, is there any kind of weather data sets that can take into account how different temperatures and things will be in the future?
Yes, there are. It's debatable of how accurate they are, and they definitely don't have the level of spatial and temporal resolution. So I think most of it's like there's this Euro Codex data set, right? I think maybe 6 hourly resolved or 3 hourly resolved. I don't know if anyone knows that. So that definitely has some coarser time resolution, and there's also quite a bit of noise between the different climate models. So I'm no expert in that. I know these data sets exist, and there have been studies done on that. Yeah, that's all I can say.
Only because if we're looking for, like, say, 20 years ahead,
yeah,
something like that,
yeah,
and we're like running out of water, so hydropower is like nothing.
Yeah.
This could affect somehow the output of the model. Like that.
Yeah, in principle, and I think AdLight used to have a feature interfacing with the Eurocodex dataset, which we removed at some point because no one was maintaining it, basically. Yeah, but we might add it back in the future. Yeah, so on the, or was there one more question? No. So, yeah.
So you mentioned that you only use 1 year for the simulation.
Uh-huh.
So how do you choose that year?
You will see, I think, a graphic tomorrow with all the sector coupling in it. But we currently use 2013 as a default year. It's like a plug-and-play change in the config file between the 7 years I just mentioned, a kind of range of kind of favorable, less favorable years. And 2013 sits somewhere in the middle, basically. Or it's kind of upper quartile, or it's kind of third quartile year in terms of how it performs in system costs. It's more of a historical choice than a conscious choice, and we haven't changed it since it kind of fits somewhere in the middle. But yeah, it's a big challenge that actually most of the analyses should be done with more than one weather years, just because the variabilities we see there are often bigger than the variabilities that we see in the other sensitivities that we do.
So, but it's chosen like, so in the range of years, we have seen like these years are more expensive to the model, no, and more cheap to the model, and you have chosen like an average on that.
Yeah, roughly, yeah.
So just to get it right, so what an acolyte does is that it takes the energy that theoretical potential, and then it applies some technical characteristics of the energy system, like the orientation of the material, and convert it
into a capacity factor time series. Yeah, like what at any hour for each region, what share of the peak production capacity of a PV panel can be produced.
And those technical parameters, they can be edited?
They can be edited, yeah. I think there's a range of, I think, probably 200 different wind turbines in there that you can choose. There's less so on the PV side. I think there's four different technologies or so, and you can choose the orientation. You can say it should be the optimal orientation. It should be south-facing, east-west facing, something like that, or tracking or not tracking. There's some configuration options there. Not as much as we should have done, but yeah, it's something we've been discussing, and we try to assess a little bit how our capacity factor time series fit with the other data sets, like the PEC-D or the ones that are used at the ENSO-E, for example, and so it's ongoing work. Yeah, they're roughly like in plausible orders, but yeah, to some it can maybe be on the high or low side depending on your perspective.
Yeah, just going on from that, is there a version of that like from, because we know where the existing wind and solar is,
Yeah.
where it only takes data from those points rather than averaging?
Yes, so that would be possible. So maybe I do one slide before that, coming back to your question, because I think it's not only a question about where the existing wind turbines are. So that's one reason why you don't want to plainly average across the region, but you maybe want to average across the locations of where the capacities are. And if you're looking more at on the potential side, you have a very similar structure that you need to know where the potentials are, and if you assume that within a region you're roughly even, within smaller grid regions you will have relatively even wind resource, and if you then assume that the capacities distribute relatively evenly, then you can use the potentials as a weighting. So the weighting, whether it's existing capacities or potentials, they can be put into AddLight kind of as an indicator matrix of how much weight should be put on every ERA5 grid cell within the region. And doesn't have to be potentials, but can be existing. I mean, one has to do one calculation step in converting the points where the wind turbine capacities are and associate that with the ERA5 grid cells. Yeah.
If you cluster power plants together,
Mm-hmm.
which capacity factors are you using from that node, or like from the area of the cluster?
So there's typically we would cluster to one representative average technology per region, which is fine if your spatial resolution is high. Which is a challenge, or maybe not so accurate, if you have country-level resolution. And in that case, there's a feature to define that's relatively new to define resource classes, so that every clustered regions, these potentials, both on the geographical potentials about the capacities, as well as then the associated capacity factor time series, they are grouped into resource classes that you have And you can say with how many you want to have of them. For example, you maybe want 10 resource classes or 3 resource classes. Then you get 3 or 10 wind generators representing each of these different classes with gradually declining average capacity factors, for example. Yeah. And that allows you to have kind of diversity in the renewable supply technologies while not having the complexities of the grid resolution. Right. The data sets that are used for that I mentioned earlier in this data outline is basically overlaying the different exclusion criteria. So in many cases, you end up with something that kind of most of the regions is excluded, and then kind of maybe 20% of these regions kind of is a typical order of magnitude. It's kind of eligible, and that area is then multiplied with an assumed deployment density. There's no, at the moment, there's no kind of explicit placement of the wind turbines, but it's just kind of taking that as an area available multiplied with a capacity density that is technology specific. Okay, so existing power plants is one of the kind of last components that we need to add to have a model. We have the renewables, we have the grid data, and now we have also some representation of the existing power plants. As another tool here, power plant matching, is because we only use open data sources, and each of the data sources that are openly available has some data gaps. So our idea was to put everything into a matching algorithm to get the best coverage of by merging all the different data sets, among them, for example, the global energy monitor I highlighted earlier. You can use that independently of PyPSA or PyPSA Europe. It's kind of also small Python packages, which you can just take pre-built and then query by some filters, maybe only newer ones that were built after 2000, for example, and you get kind of name, fuel type, technology, country, capacity, commissioning year, retirement year, and the coordinates. And the important thing here is that it also has retired power plant capacities here, so one has to be a bit careful. For example, there's still some nuclear in Germany, and the reason we keep it in this way is that maybe we want to do some backcasting for the validation of the model, and then it's important that you have kind of historical capacities still available. So we run it every time we change some of the input data, and the matching algorithm, in principle, everyone can run it themselves. It takes maybe 30, 45 minutes or so. It's not a super quick, running this matching algorithm is not super quick. And then we have, for each released version of the tool, we have kind of a pre-built data set.
And it's limited just to Europe?
Originally, yes. I think there's some developments that to extend that more globally, because kind of many of the data sets here, they have global coverage. And I think, for example, PyPSA-Eur is also using it, and it just requires changing some of the configuration files. Good. Yeah, and as I said before, or with regard to the wind resource classes, typically these are clustered per technology to the grid resolution as one representative technology, just to save some decision variables, but there's also the option to keep them block by block, basically.
How that matching, how does it deal with possible inconsistencies in the data set? Because you're relying on different sources, and maybe they don't have the same information.
Yeah, so there's a manually set ranking between the different data sets, like a trust index, where this is just our experience. So there's no formal method behind it, but for example, we know the global energy monitor, what it has is typically very correct. And then there are other, maybe, and also the older the data sets are, for example, the less reliable the data is, and they get a lower score, and they're prioritized less in the data sets. So this example of the Marktstammdatenregister. So it's a public registry in Germany where all the power plants from a certain size, and that goes all the way to kind of small-scale rooftop PV, have to register. And that has the highest possible score because it's a regulatory requirement that this data is collected, and we can be relatively sure that the data there is correct. Yeah.
The data from XOA, I would guess that
it's not complete. and maybe it doesn't have all the different data items here. Yeah. Yeah, we would welcome somebody who knows the system to check that. But I mean, not that you don't get that feedback directly, but in the match data set, you can see which originally data items were used, and you can kind of trace back which of the merged attributes were used and where they might deviate from one of these data sets here. So you can it's traceable, but it's not checked individually on a regular basis by us. We check the aggregate statistics per technology, per country. That is our validation that we do. Everything else we currently don't have time for. Okay, so now it's time to pull everything into the model, and there's one last bit of data that we need to bring in. We need to make some techno-economic assumptions, and for that we rely heavily on the, I guess, many of you will rely on the same kind of data sources like the Danish Energy Agency technology catalogs, taking the different investment costs, fixed operation maintenance cost efficiencies, and lifetime. But we also kind of, for different years, but we also mix in other data that we need from other sources. So it's kind of Danish Energy Agency first, which is nice because it comes from the same data source. So hopefully, or at least the task of making a consistent data set is outsourced to a large extent, and then we only supplement with some bits that are missing for our model. Right. So I think we should, yeah.
Just a quick question on the technology data.
Mm-hmm.
More pushing like the latest version to do some test runs to check that it's still consistent and you don't suddenly get good results out.
Yeah, we haven't done so much in the past, more intermittently, and more when kind of we were using and we wanted to check is it still good. But now we have a software engineer in our team, and we're professionalizing that a little bit. So, and it's important that we check that. So we definitely want to do it, at least the aggregate statistics.
Can you select optimistic, conservative, and pessimistic?
Yes. So you can, from the Danish Energy Agency, you can select the optimistic, pessimistic, and central columns. But I think that they don't exist for all the different years. I think in the Danish Energy Agencies, the optimistic, pessimistic, they are, I think, for, correct me if I'm wrong, but I think they're mostly for the 2050 time horizon, right? Yeah, exactly. Yeah.
And are these assumptions configurable? Like, can you change the assumptions for whatever technology that you're looking at?
There are parts of it that you can configure directly in this database. It's like what reference currency year do you want to use, like 2020 or 2015 or something like that. And there's an opportunity to just download this data set and edit the CSV directly in your workflow and kind of reference that as your custom cost file. Or kind of completely rebuilding this data set is also an option and referencing that, but I probably wouldn't recommend that because I don't think you want to go through thousands of techno-economic settings, but there's room to just, once you have downloaded it, to change some of the values as you see fit. Yeah, so the conventional storage is there. We haven't added the battery storage yet, just because until 2 years ago it wasn't super relevant to kind of go with a greenfield approach on the battery side. But the pumped hydro is there. Yeah. Yeah, so I think on the hydro side, we're not as detailed as some of the other energy system models. So there's no kind of link between the river reservoirs, for example, and between the different hydro plants. So it's mostly working with annual inflow statistics of the power plants to determine the dispatch. Yeah. So it's relatively simplified. It's just making sure that the kind of annual power production from the hydro per hydropower plant roughly matches what we've seen in the past. And that is then adjusted for by the runoff from the weather data. But yeah, it's not like an interlinked model between the hydro reservoirs. I should maybe wrap up soon to take a break. And get you working as well after that. But maybe the last thing I want to mention is that here we have talked about spatial aggregation as well. We've now added the different time series for the renewables. Also, I didn't mention that in too much detail, but also the demand for the electricity, which is not that exciting because it will be exciting on the sector coupling side, but on the electricity side, we just take the current profiles from the NSOE transparency platform, and assuming that as an inelastic demand. But on the temporal aggregation here, we don't work with typical days, for example, or we don't work, typical representative periods. We always keep kind of as the sequence of the different hours, but there are different ways of aggregating the hours. So we can do kind of averaging every nth hour. And that's what we typically do, because the benefit of going from computationally from 1 hourly to 2 hourly resolution is just roughly cutting the problem size in half, while still giving, we did some sensitivity analyses on that, we're still giving relatively sensible results that do not deviate so far from the hourly resolution. I would probably say that it would be more important to have 3 years of coverage at 3 hourly resolution than 1 year of coverage at hourly resolution. If you can also do a sampling where you just sample every 3rd hour, or you do nice clustering algorithms that Forschungszentrum Jülich, the research center in Germany, has put together in a time series aggregation module where you aggregate snapshots. You average snapshots, but the length of the snapshots is different. So you always aggregate adjacent time steps, but for example, during the night. So here's an example for solar where it's very illustrative, where it doesn't make sense to have temporal resolution for the solar throughout the night because the output is always 0. So you cluster 12 hours during the night and then have hourly resolution or native resolution throughout the day. So if you have a lot of different time series with a lot of different characteristics, it's not going to be that easy. But the algorithm, you give that all the different time series and still makes a similarity metric. And what it ultimately results in that you get kind of, if you want, a time series clustering that is maybe equivalent to a 3 hourly resolution, you will see all sorts of blocks between hourly lengths and 10 hourly lengths. So I think I would end it here and do the rest after a break, and show you a live demo of the workflow before you get started. But there are at least two questions.
On the temporal aggregation, when you're doing the capacity expansion modeling for all of Europe,
Yeah.
how many concepts do you usually end up having?
Yeah, so it depends on the spatial resolution, but take an example of maybe 100 regions in Europe with all the sectors represented. Then we would typically end up somewhere between 3,000 and 5,000-6,000 time steps. So that's somewhere between 3-4 hourly time steps to 2 hourly. We rarely go with the hourly resolution because the differences are really, really small between hourly and 2 hourly, even on the battery and solar feed-in. There's another question somewhere I saw earlier. Yes?
Even for batteries, it doesn't matter.
Yeah, even for batteries, the hourly doesn't matter too much. I mean, there's some slide, but it's kind of 0.01% in system cost and maybe something like order of 0.1% in capacities.
And do you then take the average or the segment?
It's up to the user, but we typically take average. So the further you go with the aggregation, you smooth out some of the variability. So if you go for 6 hourly resolution, you start getting very different results because it averages out the solar feed-in and you don't need any batteries. I think, yeah. If you dig in one of the papers we did, maybe it was, I think it was one we did on hydrogen networks. If you dig deep in the 70-page appendix, then you'll find one sensitivity analysis where we did exactly that. It's kind of going from hourly to 6 hourly resolution and looked pretty good for hourly, 2 hourly, and still for 3 hourly, but then started to deteriorate very quickly.
Did you ever think to go beyond below 1 hour?
Not really, because most of the raw data that we process is at hourly resolution, so we don't have any information about this. We can subsample that, of course, but it doesn't add any information. We can kind of interpolate between it, but we don't get more information from it.
If you had the data?
If we had the data, it would probably depend on the use case. Probably for these large infrastructure questions, I would say perhaps hourly is enough. But I haven't done it, so I can't really say. But I think if you look at more fine grain, maybe market operation as well, in 15-minute, like many of the markets we see in Europe operate at 15-minute resolution, so then there might be a strong incentive to go quite a quarter hourly resolution. And we don't model any kind of frequency reserve or things like that, so then of course there would be much more incentive to go to kind of minute resolution or even smaller. But yeah.
Like when you say like you run the model on 3 hourly basis and 100 spatial nodes, how much time it takes to run the full model?
Say again, how many?
Like how much is the running time of the model?
Okay, so then I'll actually do the slide. So it depends heavily, and it's very hard to give a rule of thumb. Generally, all the model building you can do on your laptops. We'll do a simplified version of that, but if you do kind of full Europe preparation of all the time series, the renewable potentials, maybe it takes half an hour to get to the point where you send it to the solver, where you really process all the different data sets, you do the GIS analysis of the renewable potentials and so on. And then once you go to the solving, then it depends whether you have access to a solver, a commercial solver or not. This type of problem really doesn't work with any of the open source solvers once you have the spatial resolution. And for the large scale, kind of 100 region, 2 hourly, 3 hourly resolution, and all the sectors represented, I typically aim for runtimes of 2 days per scenario, which is the kind of maximum I'm willing to tolerate. But it's my constraint because I say I want to develop, I want a certain development speed, and I don't want to wait for 5-6 days, and I'm willing to sacrifice some of the spatial, temporal, technological resolution to get to that point. So I will always kind of max it out to the time I'm willing to tolerate. You can do very nice things with models that run in an hour or two. It's not always necessary to run very high resolved models, and you get very nice inside models that run in an hour. And then once you have this commercial complicated problems, you also need a bigger kind of RAM. You have a bigger RAM requirement, which historically used to be our bottleneck, rather than the time we're willing to wait for it. Okay, I would say we do a break now. It's good that you ask a lot of questions, so I'm happy to kind of hijack the schedule a little bit. But I would say we maybe take a 15-minute break and then come back and do some, I'll do the live demo and get started with the installation before lunch.